Suppose that we have a uniform bar in outer space, so we don't have to worry about its weight because there is no large mass pulling on it. Okay, so you know, it is weightless. That means there is no gravitational force acting on it. We can think of it as at rest. Okay, so the resultant force on it is zero. Now, by a uniform bar, we mean a bar whose mass is uniformly distributed through it. So we don't have a situation where there's more mass at, say, one part of it than there is at another part. The mass is evenly distributed through the bar. Now imagine two forces of equal magnitude acting at the ends of the bar. Let's suppose that this force has magnitude 10 newtons. Now we are going to assume that these forces always act perpendicularly to the ends of the bar. So the bar will move, it will actually rotate, but these forces' magnitudes remain constant. So here's a picture of the bar sometime later. Okay, the forces have constant magnitude and are always acting perpendicularly to the ends. It's a very artificial situation. But what I want to point out here is the resultant force acting on the bar. Well, we can clearly see that the resultant force on the bar is zero. You know, the forces are anti-parallel. They point in opposite directions, but they have equal magnitude. So when we take the vector sum of these two forces, we get zero. In previous videos, we considered the forces acting on a particle. So if instead of the bar we have a particle, well, if we apply these forces to it, we get a resultant force of zero, of course. But the particle remains where it is. Whereas in the case of an extended object, this bar, it does not remain where it is, it rotates. See, the reason why we dealt with particles in previous videos is because a particle has essentially no dimensions. So we don't have to worry about the rotation of this particle. It's so small that its rotation can be ignored. In the case of extended objects, even though the resultant force acting on it is zero, we still have movement. We have rotational movement. However, there is no translational movement. The center of mass of this bar is this point here, and we will discuss center of mass in later videos. But you can see that this point is not translated. It remains where it is. So in that sense, applying Newton's second law makes sense. Okay, this point has no movement, just like the particle here remains at rest. By the way, as an aside, I should say that if these forces were suddenly to disappear, okay, if you can imagine these two forces vanishing, then the bar would keep rotating forever. Okay, it would keep rotating in this direction indefinitely. That means forever, provided that no other force acts on the bar. So the bar's center would remain fixed, but its rotation would be indefinite. Okay, so to repeat, when we look at forces acting on extended objects, that is not particles, we have to consider not just translational movement, but also rotational movement. So we have to consider the turning effect of a force acting on our extended object. In all the previous videos, we approximated our objects by particles, so we did not have to worry about the turning effect. We only had to apply Newton's second law by taking the vector sum of the forces acting on the particle. Here we have to consider the position of the forces acting on the extended object, and the position of those forces will change the turning effect of the force. So this leads us into the idea of the turning effect or moment of a force about a point. So let's look at the definition of the magnitude of the moment of a force about a point. Okay, the moment of a force about a point or axis is actually a vector quantity. Another name for it is the torque of the force. Let's look at a simple example to illustrate the magnitude of the moment of a force. Here we have a wrench and we're trying to open something, say we have a nut here and we want to turn it. We want to turn it anti-clockwise. So we apply a force to the handle of the wrench of 80 newtons. You probably know from experience that the magnitude of the force is not the only factor. It's the distance of the line of action of the force to this point that also counts. So the line of action of the force is just this line here. It's the line that the vector lies on. This force vector is perpendicular to the handle of the wrench. So to get the magnitude of the moment of this force, to stress that I'm talking about the magnitude of the vector quantity, we can use these vertical lines. We get the product of the magnitude of the force with the perpendicular distance of the point to the line of action of the force. Okay, so we want the magnitude of the moment of this 80 Newton force about this point here. Now we could also think of an axis perpendicular to the screen or the page passing through this point. Okay, so in later videos we will discuss the moment of a force, not just about a point, but also about an axis. In our case, since the problem is in the plane of the screen, the axis would be perpendicular to the screen. It goes into or out of the screen. Anyway, all we have to do is multiply 80 newtons by the perpendicular distance of the line of action of the force to this point, which is 0.4 meters, because the force acts at right angles to the handle of the wrench. So it's just 80 multiplied by 0.4, so we have 80 newtons multiplied by 0.4 meters. So you can see that the unit of the moment is going to be Newton meters. So we get 32 Newton meters. By the way, to get a feeling for what this force is like, as an aside, I will mention that a force of 10 newtons is approximately equal to the weight of a bag of sugar. Now a bag of sugar has a mass of 1 kilogram. So the weight of a bag of sugar is mg. So if the mass is 1, the weight W is 1 times g. That's 1 times 9.8, or 9.8 newtons, which is approximately 10 newtons. So the force that's applied here is equivalent to the weight of 8 bags of sugar. Now let's consider this situation here. The same force of 80 newtons is being applied, and this time it's at an angle that's not 90 degrees. Let's suppose that the angle is 30 degrees. So how do we get the moment of this 80 Newton force about this point here? Well, we need to get the perpendicular distance of this point to the line of action of this force. So now the perpendicular distance is this distance here. So how do we find this distance? Well, we can see that it's opposite 30 degrees in this right angled triangle. So we have to multiply the hypotenuse of the right angled triangle, 0.4, by the sine of 30 degrees to get this side. The sine of 30 is 0.5, so we've 0.4 by 0.5, that's 0.2 meters. So now we see that the moment of this force has decreased. So the angle is important, obviously. We have a smaller turning effect due to this force here at an angle of 30 degrees. Let's take an extreme situation. Here the 10 Newton force is applied in the direction along the arm of the wrench. Now it's no surprise that the turning effect of this force is going to be 0. Look at the line of action of this force. We can see that it actually passes through the point. So the perpendicular distance of this point to the line of action is 0. So we end up getting an answer of 0 Newton meters. The same is true, of course, if the 10 Newton force is pointing in this direction. We know from experience, of course, that if we were to pull on the handle of the wrench, that it will give no turning effect to the nut. Here is another situation that we could consider. So the line of action of the force looks like this, and we want the perpendicular distance of this point to the line of action. So let's suppose that this angle here is 30 degrees. Well, that means that this angle is 30 degrees. These are opposite angles. So we'll get the same result as we saw earlier actually. We multiply the hypotenuse of this right angle triangle, which is 0.4, by the sine of 30 degrees. And that gives us 0.2 meters. So like before, where the force was applied in this direction at an angle of 30 degrees here, the moment of the force is 16 Newton meters. So we can see that it's clear for this situation that the force that we applied must be applied at right angles to the arm of the wrench. That gives us the maximum moment of the force, or the maximum torque, which in this situation is 32 Newton meters. Another way to increase the torque, or moment of the force about a point, is to increase the perpendicular distance of the line of action of the force to the point. So we could increase the length of the arm of this wrench by slipping over the end of the wrench a hollow pipe. So we can extend the arm of the wrench. So let's suppose we double the length of the arm from 0.4 meters to 0.8 meters. Well, you can see now that we've doubled the torque or moment of this force of 80 newtons about this point. It went from 32 Newton meters up to 64 Newton meters. So now we have twice the turning effect for the same force of 80 newtons. So we do not have to apply a greater force to increase the turning effect or moment of the force. Now let's consider the vector aspect of the moment of a force about a point. In this course we will only deal with planar problems. So that is problems for which all the vectors involved are in a plane, and also the object lies in a plane. So to get a picture of what's going on, I'm just going to try and draw a plane in oblique view, because I want to show vectors lying in it, and I also want to show vectors that are sticking out of it. Actually, the vectors that are sticking out of it will be the moment vectors, which we won't be drawing in general. I just want to mention that, the moment vector is a real vector, but the vectors that we will be showing, of course, will be the vectors in the plane of the problem. So we can take a point A and we consider some force lying in the plane. Let's say that this force is F. So here we have our objects, vectors, points, bars, whatever, lying in the plane. So let's consider the moment of vector F about the point A. We will call that moment vector M. And first of all, we will get the magnitude of that moment vector. Well, we know how to do that. We have to multiply the magnitude of the vector F by the perpendicular distance of the point A to the line of action of vector F. So let's suppose that this perpendicular distance is d. Now we are looking at the moment of a force about a point purely abstractly. We haven't mentioned what the object is. The object could be a bar passing through the point A and through the line of action of the force, or any object. So we have the turning effect or moment of vector F on this bar about the point A. And notice that it doesn't matter at what angle the bar passes through the line of action of F. Bar could look like this, and the moment is still given by F times d. Now, the moment of a force has two directions, which are indicated by a plus or minus sign, for a force with an anti-clockwise or clockwise turning effect, respectively. So let's look at the turning effect of this force F about the point A. Well, we can see that if we're looking down on the plane, the turning effect is in this direction. And this direction is anti-clockwise, against the clock. Okay, so we're looking down on our plane. So this is our page, or for my case, the screen. Okay, we're looking down in this direction. So F acts to turn whatever the object is anti-clockwise about the point A. So now if we want to talk about vector M, we just deal with this positive quantity. Well, F and D are just magnitudes, so they're automatically positive. But the moment vector will be positive. You can put a plus sign in to emphasize that if you like. Now, the plus sign is just a convention for an anti-clockwise turning effect. We could have used a different convention. We could have used a minus sign. That doesn't matter actually, as long as the clockwise moment has the opposite sign. However, we will see later that using a plus sign ties in well with conventions for the direction of forces and the direction of position vectors in a plane. I'll get back to that later. Okay, so this is our vector M, but where is vector M? Well, as a matter of fact, vector m is perpendicular to the plane of the problem. So that's why we never show vector m. If vector m is positive, that means we are dealing with an anti-clockwise moment, then vector m actually points out of the plane. So if I can try to show that, vector m would look like this. But remember now, it's not in the plane, it's pointing out of the plane, so it's perpendicular to the plane in every direction. So that's pointing up out of the page, so obviously we cannot show that, and we do not worry about that aspect. We just consider the sign. Now let's consider a different force. This force F has the same magnitude as before, and it's on the same line of action as the previous force, but it points in the opposite direction. The magnitude of the moment of this new force is still given by F times d, like before. It's a positive quantity. That hasn't changed. But what has changed is the direction of the moment vector. We can see now that the turning effect is clockwise. I'll do that in blue. Okay, the turning effect of the force vector F about the point A is clockwise. That is if when we're looking down on our page, the direction is in the direction of the clock, motion of a clock. Okay, so for that situation we use a minus sign. Okay, so a minus sign for a clockwise turning effect. So F times d is the magnitude, same as before, but now we stick a minus sign in front. Alright, so that's how we will write vector m. Again, like before, we will not be showing vector m. In this case, actually, vector m is pointing into the plane. So it would look like this. See, there's only two directions to consider. Either the moment vector is pointing out of the plane at right angles, or it's pointing into the plane at right angles. So when it's pointing out of the plane, it's positive, and when it's pointing into the plane, it's negative, but we don't have to worry too much about that aspect. I mentioned earlier that the sign convention for the moment vector m ties in nicely with the usual sign convention for vectors in the plane. That is, vectors pointing to the right are positive, usually, and vectors pointing upwards are positive, usually. Just to see why that is so, we can consider, say, force acting on this bar, and we're interested in the moment of the force about this point here. We can call this point A. Now we can set this point to be at the origin, 0, 0. Okay, and we have some force, let's say it's acting upwards. So that's in the positive direction. So F is greater than 0. Let's make the perpendicular distance of the line of action of the force 2AD. For convenience here, I'm making F perpendicular to the object. And you can see that D is positive. Okay, so we're taking the moment of this force about the origin. So this point here is to the right of the origin, so it's positive. So we can think of D as a vector as well, the position vector of this point here. Just make that more clear. Okay, so what's the moment of F about this point here? Well, we simply just multiply F by D and we'll get a positive answer, and that ties in with the fact that an anti-clockwise moment is positive. Okay, so this force will have an anti-clockwise turning effect about point A. So we can just multiply F by D. You can put in a plus sign to emphasize that we have an anti-clockwise turning effect. Now let's consider a force F acting in the opposite direction. So this time F is negative. It's pointing downwards. That's negative. That's the negative direction. D, however, is still positive. Okay, so what about the moment vector? Well, we just multiply F by D. And this is going to come out to be negative, because F is negative. Okay, if we're dealing with the vector F. Don't get confused here. If I put in the minus sign, I'll actually make it positive. So it's just saying here that F itself is actually negative. So you can see the moment vector will come out to be negative, and that's what we want, because we have a clockwise turning effect here. So we have a clockwise moment which is negative. Now here we could consider a different situation. So we have this bar or object or whatever, and A is at the origin. In this case you can see that F, since it's pointing upwards, is positive, but D is now negative. Now what's the turning effect of this force about point A? Well, we can see what that direction is. Well, we can see that it's clockwise, which is negative. Okay, that's the convention to make a negative. And that ties in with these, because if we multiply F by D, we get a negative result. So M equals F, which is positive, times D. Now the position vector D is negative, if we think of D as a vector. So this will come out to be negative. That's exactly what we want. And finally, the last case, I might as well finish it, is the situation where F is pointing downwards here. Now you can see that both F and D are negative. So the moment of the force is got by multiplying these two. Think of them as vectors now. So negative times negative is positive. So this will come out to be positive. And that's exactly what we want, because the turning effect here is anti-clockwise. And an anti-clockwise moment is assigned a positive sign.